Hello, everybody. Thank you for coming to our presentation. We are here to give you a quick overview of our project, which is going into detail about fluid mechanics of endotracheal tube.
So, how are you feeling since the last procedure, patient?
Better. Could you tell me what the problem was?
Sure. Well, we found you roadside against the hospital, probably overdosed on drugs, but you couldn't breathe, so I used this, an endotracheal tube.
One? Do you store it there?
Well, for the purpose of this video,
right.
I do. Anyway, yeah, so this is what saved your life. It helped you breathe because you couldn't do so on your own.
How does it work?
Well, if you look closely here, this is the whole tube, and I put this, essentially everything underneath this cap inside your larynx or windpipe. And then what I did after that was, since this is outside of your body, I inflated it, and then what I can do is inflate the cuff. So once this inflates, it essentially traps or seals the trachea, so air could only go through here, and this can connect to the ventilator to allow oxygen to transport much more easily.
Yeah, that means nothing to me. You want to explain? It's interesting, but it means nothing.
Sure. Well, there are 4 biofluid mechanics principles involved with this particular device. The first one is the ideal gas law. The second one is the relationship between volume and pressure of the cuff. The third one is the hydrostatic pressure of the fluid within this cuff, which is actually the most important piece of this device since it seals the trachea. And the fourth one is the relationship between force and pressure of the tracheal wall against this cuff once it's inflated. My colleague actually has PowerPoint slides detailing all of these theories and considerations if you're ever interested.
There are several components for the device. The first one is the tube itself, which is made out of polyvinyl chloride, and the location is within the trachea. And the second component is the cuff, which is made out of, same thing, polyvinyl chloride. However, this is the main fluid mechanics component of the device. And the two problems associated with it is overinflation and underinflation. And if you look into the image to the right, you can see the tube and the cuff itself. The first principle that I want to get into is the principle of ideal gas law, which basically talks to you about the pressure within the syringe itself and within the cuff. So this is governed by the ideal gas law, which is PV equals nRT, and also P1V1 equals P2V2, where P stands for the pressure within the cuff itself, volume of air or water, the number of moles of the quantity, R is the ideal gas law constant, and the temperature which it is being governed by. The second principle involved for the cuff is the pressure generated within the cuff due to hydrostatic pressure, as well as the deflection it causes on the cuff due to it being inserted within the tracheal wall. So as you can see from the equation, P2 gives you the pressure of the cuff itself, and P2O is the pressure of the fluid at the edge of the container. Rho is density of water, or whatever fluid is being used to inflate the cuff itself. G is acceleration due to gravity, and ZO is the initial location of the edge of the cuff from the center, and Z final is the final location of the edge of the cuff after deformation. So the idea is, due to the deformation of the cuff, due to the cuff being attached to the tracheal wall, it will create a higher pressure within the cuff itself. The next principle that the cuff pressure is being governed by is the volume of fluid within the cuff itself. As you can see, cuff is made out of a very malleable product or material, therefore compliance is also very important. So as you can see from the equation, the 3 governing principles that drive pressure within the cuff are the volume of product or fluid within the cuff, the area of the cuff being exposed to the tracheal wall, as well as the cuff compliance. These 3 parameters come together to create the pressure within the cuff wall, which holds the endotracheal tube in place, prevents it from falling into the trachea. The final and probably the most important fluid mechanism for the endotracheal tube is the flow of air within the tube itself. As you can see from the equation, QA stands for the air flow rate, pi is just pi, velocity of air, and the diameter of the inner diameter of the tube itself. And these are the major governing factors that influences the flow rate of air through the tube itself. For these patients, mostly it's being governed by the ventilator itself, and it's manually controlled. Thank you for listening to the presentation, and have a good day.